Okay, great. Welcome everyone to the third webinar in the 2021 EERI Distinguished Lecture Series with Dr. Craig Davis, Lifeline Infrastructure System, Functional Recovery and Operability. I'm Elizabeth Angel. I'm the Communications and Coordination Program Coordinator at the Earthquake Engineering Research Institute. For those of you who aren't familiar with EERI, I want to say a few words before handing things over to today's moderator. The Earthquake Engineering Research Institute is the leading nonprofit membership organization dedicated to understanding earthquake risk and increasing earthquake resilience in communities worldwide. EERI has been bringing people and disciplines together since 1948. By joining EERI, you become a member of a global network of multidisciplinary professionals dedicated to reducing earthquake risk. The support of EERI members also helps make events like this one possible. So now I'm going to turn things over to today's host and moderator, Divyansh Kapoor, who will be welcoming you on behalf of the New England Regional Chapter and the Student Chapter at the University of Massachusetts at Amherst, who are hosting this session. Divyansh, take it away.
Thank you. Good afternoon, everyone. My name is Divyansh Kapoor, and I am the chapter president here at UMass for the graduate chapter. I'm joined by Hernan and Thomas, who are also on the leadership board here. And I'd like to welcome you all to the third panel, the third Lifeline Infrastructure System Operability panel. We, in addition to our graduate chapter, we also have a very strong, could we go to the next slide? We have a very strong undergraduate seismic design team that participates in the annual competition each year. You can see some of them in the top right, and this was actually the design they came up with last year. I had the pleasure of seeing them present live on Zoom when they presented. They're very active. They have, I've been working with them for the last year and a half, and they do some really cool work. So each year they design and build a 5-foot tall balsa tower that's capable of withstanding seismic loading. Most of the work is done in industry standard software like SAP 2000 and AutoCAD and SketchUp. And this really helps them learn about some advanced concepts of earthquakes and earthquake design and seismic loading, which otherwise they wouldn't get to until much later in their graduate studies. If you're interested in joining the team, here's some further information about them. And yeah, like they say, all grades are welcome. And with that being said, I would like to introduce Dr. Craig Davis today. He is this year's Distinguished Lecture Award winner, and he's a professional geotechnical earthquake and lifeline infrastructure consultant. Prior to starting his own firm, he worked for the LA Department of Power and Water, where through his roles as Department Chief Resiliency Officer, Seismic Manager, Geotech Engineering Manager, he systematically planned and improved the resiliency of their water pipeline system. In addition to this, he also serves in several committees, such as the Building Seismic Safety Council, National Earthquake Hazard Reduction Program Advisory Committee, and the ASCE Infrastructure Resilience Division. He's been honored with several awards throughout the years, such as the ASCE Leva Lund Award in 2016 and the Charles Martin Duke Lifeline Earthquake Engineering Award in 2020. And we're very fortunate today to have him here, and he's going to share some of his fantastic experience with us. And with that, let's take a look at the recording.
Hi, my name is Craig Davis, and today I'm going to present to you on Lifeline Infrastructure System Functional Recovery and Operability. This is an EERI Distinguished Follow-Up Lecture. The 2021 EERI Distinguished Lecture, titled Operationalizing Lifeline Infrastructure System Resilience to Earthquakes, was given on March 24th, 2021. It is available on the EERI YouTube site shown on this slide. This current lecture for the New England chapter of EERI provides more detail on system functional recovery and operability. It is a standalone presentation, but does draw from the main lecture. The contents of what I'm going to present today include Lifeline Infrastructure Systems overview, the idea of functional recovery, some basic intended functions and basic services concepts, a case study on the Los Angeles water system for the 1994 Northridge earthquake to exemplify some of these concepts, the relationship between basic service categories, operability, functionality, and functional recovery. Then I'll give you some recommendations for improving functional recovery time that comes from the FEMA NIST 2021 report that I'll introduce to you. Then some conclusions and references. The purpose of this presentation is to explain some fundamental perspectives. Now, these perspectives are mine and don't necessarily reflect those of others. I will describe what we know about system operability that will aid in addressing functional recovery and identify some future work needed to progress the implementation of recovery-based objectives. So first, Lifeline infrastructure systems. Let's start with the broader category of infrastructure systems, which are the physical and organizational structures and facilities needed for the operation of a society or enterprise. Lifeline infrastructure systems are a subset of the total grouping of infrastructure systems and include water, wastewater, stormwater, electric power, communication, gas and liquid fuels, transportation, and solid waste. So now I want to introduce to you a report titled Recommended Options for Improving the Built Environment for Post-Earthquake Reoccupancy and Functional Recovery. It is a report published in January of 2021, earlier this year, by the Federal Emergency Management Agency and the National Institute of Standards and Technology. It's available at this URL that I show on the slide. In that report, they talk about reoccupancy, which is for buildings, and functional recovery, which is both for buildings and lifeline infrastructure systems. So I'm not going to talk about the reoccupancy, but in this report, functional recovery is defined as a post-earthquake performance state, my emphasis added, in which a building or lifeline infrastructure system is maintained or restored to safely and adequately support the basic intended functions associated with the pre-earthquake use or occupancy of a building or the pre-earthquake service level of a lifeline infrastructure system. So this presentation focuses on lifeline systems, so I have grayed out the words in this definition that relate directly to the buildings. The report goes on to explain how basic intended functions are less than full pre-earthquake functionality. Functional recovery is a state before achieving restoration of full functionality. Full functionality is a state achieved when all repairs are completed to the system. And the functional recovery concept is implemented using an objective to achieve the functional recovery state at an acceptable time following a specified earthquake intensity measure used for design. The acceptable time for functional recovery might differ for various building uses and occupancies or for various lifeline service users. Functional recovery requires the design of infrastructure systems for recovery-based objectives. It goes beyond the life safety and property protection objectives that we commonly use, and thus functional recovery requires us to think beyond current codes and standards, which are mostly limited to safety-based objectives. Functional recovery is a performance state when the infrastructure system basic intended functions are restored sufficiently to support the provision of the basic services needed by customers and users to undertake their basic intended functions and provide their basic services and products. The basic intended functions provide users the minimum level of services needed so they can undertake their activities in a relatively normal manner. The current challenges to accomplishing functional recovery are the identification of what basic services are needed by whom and when, what basic intended functions are required to deliver these basic services, and how to define recovery time objectives. I'm not going to give solutions to these challenges, but I am going to introduce some information that will be helpful as we move forward to finding the solutions to these challenges. But to understand functional recovery for infrastructure systems, we need to recognize the fundamental concepts of function, along with its derivative terms, functional and functionality, basic intended functions, and services provided by infrastructure systems. So function is the action for which an infrastructure system is used to deliver a service. That is, what is done to deliver the service. Basic intended functions are the actions to provide the basic services. A service is what is provided as a result of the functions undertaken. So basic services are the most fundamental services needed by the customers and users. To give an example, I show you here some water system basic service categories. And to explain this, I want you to understand that on a normal day, when there is no disaster prior to that day, we normally go in, we turn on the tap, we see what we would consider the results, the product of the service. We would consider it as one service provided by the water system. However, there's actually at least 4 services I pose. And in a disaster, so after a major earthquake or other significant hazard that can damage a water system, we need to think about them in terms of 4 different service categories. And those are water delivery, quality, quantity, and fire protection. I give some technical descriptions in the table on what these categories mean. But in general, you can think of them as whether water is coming out of the tap, safe to drink, and you get the amount of water you need, and does a fire department get what they need? I'm going to explain this in greater detail and also introduce the concept of operability in a case study of the Los Angeles water system and its performance and response and recovery after the 1994 Northridge earthquake. So the 1994 Northridge earthquake struck northern Los Angeles area on January 17, 1994 with a magnitude 6.7 earthquake. It affected millions of people with strong shaking. 670,000 residents in the city of Los Angeles were without water shortly after the earthquake. And another 180,000 people in Los Angeles had reduced pressure. This is a map of the Los Angeles water system, the boundary which covers the entire city of Los Angeles. Here we show the epicenter in the San Fernando Valley in northern Los Angeles. Here's the fault that ruptured in its direction and the damage, this most significant damage area. This is a map showing the damages to the city of Los Angeles water system, which resulted in 14 repairs to raw water pipelines, 80 repairs to transmission pipelines, over 1,000 repairs to distribution pipes, over 200 service connection repairs, 7 damaged reservoirs, half of the treatment plant was out of service, power was lost for up to 27 hours at different parts of the system, but there was no damage to pump or chlorination stations. Now this slide shows on the right an image of the city of Los Angeles and the water system and the blue pipelines, and the red lines are the highways. The red dots are damaged facilities to the LA water system, and the shaded areas, yellow and pinkish, are the areas that lost water after the earthquake. The yellow area had water restored within a day. The pinkish area had water restored between 1 day or after 1 day, so between 2 and 7 days. The plots on the left side are those basic service categories I just previously defined. And what we find is for the LA water system that water delivery was lost to 20% of the people immediately after the earthquake and was restored in 7 days. The water quantity and fire protection was lost to 30% of the residents in the city of Los Angeles, so the customers, and they were restored between 8 and 9 days. Water quality was lost to 100% of the customers simply due to the issuance of a boil water notice across the entire city of Los Angeles. So by definition of water quality, when you issue a boil water notice, you're letting people know that the water might not meet state public health requirements. But soon thereafter, they realized that about half of the city that should not apply because the damage did not affect the entire city. So they removed it. And then for the following 12 days, they continued working and making repairs and removing the boil water notice to different customers until at 12 days, the entire city had the boil water notices removed and all customers were receiving water meeting public health requirements. So what these plots show is that those basic service categories are measurable and can and mean something. So we can actually measure them by tracking the data and plot them on anywhere throughout the city in different areas of the city in the different pressure zones and so on. What I also want to introduce to you is this concept shown on the black line, which is an operability curve. So operability is the accomplishment of all the basic service categories. In this particular example, it is completely bound by water quality. However, that is not going to always be the case in all earthquakes. That was just the case for the city of Los Angeles water system after the Northridge earthquake. But quantity or fire protection could also cross over and bound the outer edge of operability. So now I want to show you what happened with the functionality restoration after the Northridge earthquake. So please notice that the earlier plot was in weeks, and that's shown within the bounds of this diagram here. So that's in weeks, but this functionality plot is actually measured in years. So we're at over 6,000 days. So we're well beyond what the scale of the earlier plot showed. So as a result, the delivery, quality, quantity, and fire protection essentially plot as a vertical line along the vertical axis as shown here on the left side. So when the Northridge earthquake struck, it damaged the LA water system and functionality was lost. And then as the repairs were made, functionality was recovered. So after a few months, it reached recovery at about 90%. And then it took all the way up to 9 years to make all of the repairs that resulted from damages from the Northridge earthquake. So full functionality was not restored for 9 years, even though full operability or complete operability was completed in 12 days. So that allows us to generalize and better understand the concepts between the difference in concepts between operability and functionality. So operability is achieved once water delivery, quality, quantity, and fire protection services are restored. The system is able to provide the basic services to customers at pre-disaster levels. However, the system may not be fully functional. So for example, the LA water system restored operability in 12 days after repairing 8 of 80 transmission line breaks. So the transmission lines are the large diameter pipes, and in Los Angeles, they range between 2 feet in diameter and 12 feet in diameter. So only 10% of those large diameter pipes were required to be repaired after the Northridge earthquake to restore complete operability. So operability should be considered as a measure of resilience to support the community. Now, functionality describes the ability of a system to reliably perform. A highly functional system can provide all the basic services from a Lifeline system prior to completing all infrastructure repairs. But damage imposes constraints that do not allow the system to function with its pre-earthquake performance and reliability. The LA water system restored functionality in 9 years after repairing all necessary damaged facilities, and functionality should be considered a measure of the system resilience. This slide shows a conceptual representation of system functionality and operability. So just following up on what I explained in the previous slides, so a system is functioning at the pre-event level, which is the blue line at 100%. Then an earthquake event or some other event could occur, damage the system, reduce its functionality, and then restorations and repairs will be taking place, and the recovery of functionality would follow the solid gray line. Once it reaches full functionality, it might be further improved along the stretch called R1, or it could maintain at the pre-event level at R2, or sometime during repairs, maybe not everything is restored to the way it was, and then follow trajectory R3. The operability curve and concept does not have to follow the full the functionality restoration curve, and it's shown in the orange line. And so just as explained for the LA water system, operability completely restored before all the repairs are made. So now I'm going to show you on the next slide a blow up of this portion of this diagram. So this is the same diagram. It's the same functionality and operability curve, but superimposed on this, I show 4 basic service categories labeled BSC 1 through 4. Think of those as similar to the water system basic service categories that I previously showed. So what we find here is that as the repairs are made, different basic service categories can be restored at different times based on the levels of repair. So then what that means is that the basic intended functions that are restored to provide basic service categories 1 through 4. And what we also show is that full operability is restored at 60% functionality on this particular example. So further, what we need to understand is that more work is needed to define when a lifeline system reaches the functional recovery state. So for example, what I show here is that we would know that the system is functionally recovered once operability is completely restored. And that is because the lifeline basic intended functions are restored to support the pre-earthquake service level to all customers. So that comes directly from the definition of functional recovery I gave earlier. But we can also look at it from a customer perspective. And in this range that I show between the event and the time for recovering or completely restoring operability, that can vary by user. So if a user only needs basic service category 1, but not the others for them to undertake their operations, then they would be restored much sooner than the full operability timeframe. If they needed 2 of those, say basic service categories 1 and 4, then they would be restored at that time and be able to undertake their services. So at least we would know several concepts. One is that different customers may receive their services from a lifeline system, which changes the ability for them to be functionally recovered. And this diagram shows that we need to understand and define what perspective. Is it for defining functional recovery? Is it the perspective of the lifeline system, which is item 1, or is it the perspective of the users and their needs, which is item 2? And then lastly, what we would know is that the functional recovery state is reached at before the time operability is completely restored. Now here I show, and I'm going to quickly go over this, a table of lifeline basic service categories for all of the lifelines shown in the left column. And on the top, I show the range of different basic service categories that are associated with them. Those boxes having an X in them correlate the lifeline system to its basic service category. So for example, water has delivery, quality, quantity, and fire protection along the first row. You can understand those for the rest of the lifeline systems just by looking through this table, but I'm not going to describe them in great detail. And then lastly, all of those can be clearly described and understood, but I don't have time to go over this. What I want to do now is go back to the functional recovery report, which was recently published earlier this year by NIST and FEMA. And they have 7 primary recommendations, of which I will briefly cover. They cover the need for a framework, addressing new buildings, existing buildings, lifeline infrastructure systems, recovery planning, education and outreach, and financial objectives. I will only address recommendations 1 and 4 because those deal directly with lifelines. The rest cover other items. So recommendation 1 is to develop a framework for post-earthquake reoccupancy and functional recovery objectives. It has 3 tasks. 1, to develop a policy for recommended recovery-based objectives. A second task to develop design criteria for achieving recovery-based objectives. And the third task to determine appropriate hazard levels for recovery-based objectives. And these intend to provide consistency between buildings and lifeline infrastructure systems. Recommendation 4 is to design, upgrade, and maintain lifeline infrastructure systems to meet recovery-based objectives. There are 4 tasks. 1, to provide federal and state level guidance on regulatory authority across lifeline infrastructure systems. 2, to evaluate the ability of lifeline infrastructure systems to meet recovery-based objectives. 3, develop national level seismic design standards for lifeline infrastructure systems to meet recovery-based objectives. And 4, create regional lifelines councils. So if you want more detail, there was on those recommendations. There was a recent webinar sponsored by FEMA, which is available at this highlighted URL. This webinar was produced by the Lifelines 2021-22 conference, which will be held in Los Angeles on January 31st to February 4th of 2022. Please consider attending. And this webinar and the conference itself was organized by ASCE and UCLA. So in summary, functional recovery is a bridge to implementing community resilience. It is a performance state when the infrastructure system basic intended functions are restored sufficiently to support the basic services needed by users to undertake their basic intended functions and provide their basic services and products. Functional recovery is achieved before the full functionality state, that is before all repairs are completed. Functional recovery is closely related to system operability, that is when all basic services are restored. To understand the relationship more, we need to do some more work and some more thinking. More work is needed to determine how we will define when a lifeline infrastructure system has reached a functional recovery state. And there are several key recommended actions to be undertaken to improve the design of lifeline systems for recovery-based objectives. So I leave you with this list of references, which gives you more information on different aspects of what I presented earlier in this presentation. Thank you for your time.
Okay, turning it back over to Divyansh to introduce our other panelists.
Firstly, thank you, Dr. Davis, for that fantastic presentation. And as a reminder to all our attendees, if you have any questions as they come up, you can use the Q&A feature in the Zoom chat, and we'll get through them at the end when we do our panel discussion. And with that being said, allow me to introduce Dr. Potts. Dr. Potts is a senior geologist under the geology section of the Geo-Environmental branch of the United States Army Corps of Engineers. His expertise includes environmental and engineering geology and geophysics. Prior to joining USACE, he spent 19 years with architecture and engineering firms as project manager, project geologist, and in Massachusetts and Michigan, and has projects in several states and Canada and Mexico. Dr. Potts is a professional geologist licensed in New York, Tennessee, and Louisiana. He's actually an UMass Amherst alum and got his master's here, and then went on to get his PhD at the University of Michigan, Ann Arbor, where he was the recipient of the Regents Fellowship. At NAE, he serves as PM, as the project manager, as the project geologist, and the tech lead for dam safety, civil works, and HTRW projects. He's also the agency tech reviewer for dam and risk assessment and navigational improvements. Further, he's also the district quality control reviewer for dam periodic assessments and is a member of the Risk Management Center cadre and data cadre for dams and levees. So Dr. Potts, whenever you're ready.
Thank you. I'll share my screen now. Well, thank you very much. I'm Steve Potts. I'm a geologist at the New England District Army Corps of Engineers, and I hope to provide a brief overview of what we do at New England District Army Corps of Engineers. On this slide is one of our flood risk management embankment dams. I'll be mainly focused on those today. This is Littleville Dam in Western Massachusetts. And as a bit of a disclaimer, I'll say these are my opinions and this is my presentation, so I'm not speaking on behalf of the agency or Department of the Army. So on the second slide, we can see an overview of New England District, and it's just to show that we have a full service Corps of Engineers district in New England. We have many missions and we work across missions. So sometimes we're very busy, and it's just to give you a framework of where civil works fits within our missions. We also have a military construction mission, interagency support mission where we do work for EPA and FEMA. We have a regulatory permitting mission, which is probably what most of the public interacts with when they need permits. We have an environmental investigation cleanup mission for formerly used military sites, and also the Cape Cod Canal and the associated bridges. So today I'll speak about a brief overview of the New England District dams for flood risk management, some of the seismic hazard and risk in New England, and how New England District responds to potential seismic events. This is a summary of all of the flood control or flood risk management dams in New England. They reside in Vermont, New Hampshire, Massachusetts, Connecticut, and Rhode Island. And here's an enlargement of the locations of those dams. There are approximately 33 Corps of Engineers dams in New England District. They're located in the upper and Connecticut, lower Connecticut River Basin, and the Merrimack River Basin, the Thames, Naugatuck, and Blackstone River Basins. And in addition to those civil works, we have 3 hurricane barriers in New Bedford, Massachusetts, in Fox Point, Providence, Rhode Island, and in Stamford, Connecticut. So in summary, the New England District dams are in general earth fill with rock slope protection. They range from 48 feet tall to 265 feet tall. Lengths range from about 520 feet to 14,000 feet. All of the dams were constructed between 1941 and 1971. So even the youngest dams in the portfolio are at least 50 years old now. All of the dams have large uncontrolled spillways. And all of the dams are intended for flood risk management. So the primary mission is flood risk management. And secondary benefits include some secondary water supply at a few of the dams, some non-federal hydropower installations at a couple dams, and then some recreational benefits with recreational pools at some of the reservoirs. Well, currently we follow the guidance shown on this slide when we evaluate and design dams. The ERs are engineering regulations for design of civil works projects and dams. Also, we have regulations for reporting the earthquake effects, a very large regulation 1156 for our safety of dams and our risk-based approach to evaluating our dams. We have a regulation for strong motion instrumentation and monitoring of seismicity. We have a engineering manual that describes those instrumentations in detail. And then lastly, an engineering circular, which has provided us guidance for emergency action plans, incident management and reporting, and the presentation of inundation maps for dam and levee safety. So at some of our dams, we have strong motion sensors, and we have routine seismic monitoring. Those are maintained by USGS and the Engineer Research Development Center under a contract to New England District, and they perform calibration and operations and maintenance of those. In the event of a seismic event, we would have local project staff and then staff from our Concord headquarters office go to the project and do a physical inspection. And then ERDC, the ERDIC, does the conversion and the analysis of the strong motion data for us, reports that back to us, and then we would follow our emergency action plans. We've also done some site-specific evaluations on our embankment dams. When we do risk assessments, we generally refer to the USGS National Seismic Hazard Maps, the Unified Hazard Tool. And then we modify the seismic site classification using ASCE 7-16. We've conducted some site-specific seismic safety assessments for our embankment dams in the last few years to check on possible settlement or deformation of the embankment dams and general the modeling shows very little deformation or settlement. And then we've conducted a seismic evaluation of an intake tower. This slide shows the intake tower at Ball Mountain Dam in Vermont. And in general, the intake towers seem to be very robust. So at the Corps of Engineers, we take a risk-based approach to our dams and our flood risk management structures. We are now conducting periodic assessments where we do a semi-quantitative risk assessment every 10 years on each dam in the portfolio. If the risk assessment indicates that there's a elevated risk, then we move to a higher order risk assessment, which could be an issue evaluation study where we may do a quantitative risk assessment in addition to the semi-qualitative risk assessment. We've recently done a pilot project for risk-informed seismic screening so that we could prioritize our portfolio based on seismic risk rather than just seismic hazard. And the seismic risk takes into account both the hydrologic loading and seismic loading, and we have that coincident probability of loading. And that exercise was intended to identify potential candidates for site-specific probabilistic seismic hazard analyses. Our current initiatives included updated emergency action plans, risk communication plans, tabletop exercises, and functional exercises. So our emergency action plans are a 4-step process, where step 1 is the detection and evaluation and a determination of a potential emergency level. Step 2 is then the notification and communications that are appropriate for that emergency level. 3 are the emergency actions, and 4 is the resolution, follow-up, and after action reporting. And these are steps that would be conducted by our Emergency Operations Center. This slide portrays a seismic problem assessment where we categorize a potential incident as a non-breach emergency, which would be dealt with internally within the Corps of Engineers, a potential breach emergency where we need to notify our stakeholders, and then an imminent breach emergency where we have to provide notification as soon as possible to potential parties that are located close to the flood risk management structure. The lowest category is that non-breach emergency. Then the secondary category is potential breach emergency. And the last is the imminent breach emergency. And then we have a communications notification chart within our emergency action plan, and we use these procedures in the event of an emergency. Well, thank you very much for your attention. That's a brief overview of our flood risk management dams here in New England and how we address seismic issues.
Thank you, Dr. Potts, for the presentation. So with that being said, let's move on to our next panelist, Tirza Shakespeare. Tirza is representing the Massachusetts Department of Public Utilities today, and she joined MADPU back in 2020 as a public utilities engineer. The MADPU operates under the Electric Power Division within the Executive Office of Environmental Affairs for the Commonwealth of Massachusetts. Her expertise includes electrical electronics engineering with a focus on power conservation, maintenance, and integration of distributed generation resources. Prior to joining the DPU, Tirza has worked a cumulative 10 years within the power industry for New England, Massachusetts. Her titles included integrated resources engineer, resident consulting engineer, etc. Her formal education includes a BS in electronics engineering from Wentworth, and she has an MSc, is currently pursuing an MSc in power systems at Clarkson, where her graduate studies focus on holistic power system evaluation and validation, including the benefit of bridging the knowledge gap between power system stakeholders. And here's whatever you're ready.
Okay, so as a public utilities engineer for the DPU, I will be reviewing today, similar to what Dr. Potts was talking about, the emergency preparedness and response of the DPU as the regulatory oversight for the utility or power companies in the state of Massachusetts. Here we go. Okay, so as a public utilities engineer for the state of Massachusetts, our primary role and focus is the collection and analysis of data to safeguard that the electric distribution companies in Massachusetts are operated in a manner that primarily ensures a reliable energy supply for the Commonwealth. Some of the key players and stakeholders that we integrate with on a regular basis on different levels of government, so state government, the DPU is on that level, along with the Office of Environmental Affairs, MEMA, the Massachusetts Emergency Management Agency, as well as state legislators. The public utilities engineers also represent the DPU as the lead agency serving under the Massachusetts Energy Support Function Team, also known as ESF-12. This is the energy branch of the critical infrastructure subset under the Massachusetts Emergency Management Agency. So to classify an emergency event is basically widespread outages and service interruptions. So in a catastrophic event such as an earthquake, this would be something that would be categorized as an emergency event as well. Most of our focus here in New England, specifically Massachusetts, is weather related. However, classified event will be declared when one or more companies has declared the weather operations event under an emergency response plan, which I'll speak on in a moment. The event response is dependent on that declaration. And the declarations and the activities of each declaration are described in each company's emergency response plan. So to give a little bit of background, these are some of the events that have been catalysts to department issued regulations. As we are a legal regulatory agency, we also oversee their annual filing submissions. So this is where they would actually file their emergency response plan, and this is what they would need to adhere to in the case of an emergency. So to give a little background on emergency response plans, this is to ensure company preparedness in event of an emergency. So this is their plan that is filed as a docket with the state of Massachusetts under the DPU. It is filed annually, and this is governed by the department statutes and department regulations. So as the Emergency Support Function Team, ESF-12 Energy, we coordinate activities across state agencies to respond to these events. So specifically, these would be emergency events. The coordination of activities include monitoring the performance of the utility distribution system. It's also inclusive of providing hourly outage reporting information if we have reached a emergency critical level of where hourly reporting is necessary. We also take the lead on contacting other state agencies, such as the DOR and gas, pipeline safety, and engineering. So just right here, we have the Lifeline Status. This is a snapshot of one of our reports. These are the subsets under the critical infrastructure. We have transportation, communication, public works and engineering, energy, which is the subset I am a part of, and cybersecurity. So the communications we handle is basically the flow of these players. So obviously the department, the company described here is the power company, MEMA, which is the Massachusetts Emergency Management Agency, the municipalities and public officials. This would include public safety in terms of police and fire, and as well as customers. So the event reporting will begin with normal regulatory oversight. Pardon me. Normal regulatory oversight would be defined as a blue sky day. So all outages are tracked through a regular outage reporting protocol, which each company will have. They have dashboards, outage management systems that they will report their normal ongoing, regardless of weather events, interruptions, and it's just basic maintenance and operation on the system. The emergency event reports are classified under pre-event, service restoration, and post-event. So pre-event, which we'll discuss in a moment, but includes a lot of weather forecasting and monitoring, and will give way to event classification. So in event evaluation, as I discussed before in the emergency response plans that the utilities are required to provide to the department, this is how they are classified for each stage of emergency. So as you can see here, similar to what Dr. Potts was talking about, we have levels 1 through 5. So in this scenario, level 5 would be considered a blue sky day where there's none to very few outages. Level 1 would be catastrophic natural disasters. So earthquake and seismic events would be labeled under category 1. So when the utility declares this event, they would declare it as an ERP 1. Okay, so in terms of the emergency event stages, when we are activated under that ESF 12, there are some milestones, particular milestones that bring us from each event. So the primary milestone is when the company identifies that impending emergency event, so the weather storm, and they will declare that ERP. Based off of the ERP level, now the pre-event stage will begin, where we will report out what is expected to be the activities, including resource allocation, which at sometimes might require resources to be pre-staged in areas where we expect the damage to be imminent. It will also include having mutual aid or resources coming from other territories, even other utilities, to provide support and assistance for restoration activities, depending on how much restoration is anticipated. The next milestone is the emergency event, the first moment where the actual damage is taken onto the system. That would classify when the restoration time, or excuse me, when the restoration stage would begin, not the time. That is very specific to when the actual restoration can begin, which would mean when it is safe to operate or safe to restore the system. So the next phase is the post-event stage. So before that can happen, service has to be restored to all customers. And we are talking about function and operability. So as I stated before, the emergency event stages activities, they include an incident command system. So this is where when the company has activated their emergency response plan and declared what level they are at, they will activate an incident command system within their company, which I'll give you an example of in a moment. Weather forecasting is very important during this time. Public service announcements. So they will warn any critical Lifeline customers, any life support customers, critical facilities, hospitals, as well as police and fire. The service restoration stage is very important as well. With restoration planning units, they will assess damage. They will develop estimated times of restoration, and this is something that is also defined in the company's emergency response plan, and this is something that the DPU does observe and monitor during the event classification, because if an event classification is defined as something more major or more less major, it will be we will be looking to have the companies adhere to what they have pre-stated in their emergency response plan. So the service restoration would obviously include priorities, critical facilities lists, and the post-event stage would be making those temporary repairs. So what restored functionality, we are now looking to make them permanent. So in terms of sometimes there are line switching operations that happen, there are temporary solutions, whether generators or things like that, to restore power in an emergency situation, but it's not necessarily reliable. So obviously once that stage has been set, the temporary repairs now need to be made permanent in order for us to define that everything has been restored. The post-event will be reported and it's filed 30 days after the restoration is complete. Okay, so as stated before, this is the incident command system. So basically, all of the power companies, when they have declared an ERP, they will be activating this system here. So basically, this is where the boots on the ground meets the higher executive reporting. So where we have so many different areas, territories, and functionalities of different crew members within a utility, this is the chain of command, essentially, to funnel the information back up to the executives, and the executives are the ones that liaison or communicate directly either with the DPU or the other regulatory agencies, as well as NEMA. Ultimately, a very important function is the restoration planning unit. So this unit is a unit that is within the power companies. They will have designated crews, and their responsibilities, and these incident commanders will take the initiative on the damage assessment and the restoration priority. So the restoration priority is always going to be public safety. Public safety is a wires down situation where in that regard, it would be more than likely an imminent hazard, risk, or danger to the public. So if it is an energized line and it is down, it is an imminent danger to the public safety. Second to that would be transmissions, circuits, transmissions, and substations. These are to be able to restore power to large areas and large line communities, distribution, substations, mainline feeders, and critical facilities. So critical facilities, as I mentioned before, include hospitals, fire and police stations, restoration staging areas, communications facilities, and critical care customers. Now, in a wires down situation, this is a public safety situation. So this would be something that would likely be reported by somebody in the area as an emergency event through 911. So in that situation, that would be communicated with NEMA with a direct line, and the categories of the priority would be established between 1, 2, or 3. 1 being a life-threatening imminent danger, and priority 3 being non-threatening electrical hazard. So overall, we do provide mostly administrative oversight, but where we do hold the requirement and create the guidelines and the statutes for each of the power companies to have this emergency response and preparedness, we do technically review it as public engineers. We ensure that it is filed annually and any changes are adhered to specifically in an emergency event. And that's my overview. Thank you.
Thank you very much for that, Tirza. And this brings us to the final part of today's webinar. We're going to move into the question and answer panel session. And as you have questions, please type them in the question in the Q&A box. And if you would like, you could direct it to the panelist. So you can directly say for Dr. Davis or for Dr. Potts or for Tirza. If you like a general question, just put it in as a general question. And at this point, I would like to invite all our panelists to turn on their video and start. Yeah.
I have a question.
So yeah, Lopert, we'll start. So I have a question from our live audience.
Thank you so much for all the presentations. Very interesting topics. I'm curious is about this one probably is going to be from the first part when Dr. Davis was showing us the course for operability and functionability, right? Like how those curves they can be affected based on available resources. And saying available resources, let's say, can be economical or manpower. So I can imagine that it plays an important role on how quick, right, the time that is going to be spent, right, to recover is going to be affected, I guess, based on that. And at the end, who would be like responsible, right, if they are going to be the same companies, or does it have to be, I don't know if the states, they have allocated like a resource for emergencies that they can immediately be used or something like that. So how that it can be affected in those curves.
Divyansh, could you summarize the question? There was a little bit of feedback and I couldn't hear all of the words.
Yeah, sure thing. I'll paraphrase. In summary, so how is response typically dealt in different states? And, you know, are there dedicated resources for recovery that you have in place that would be mobilized in case an event like this occurs?
There are guidelines set by FEMA and administered by FEMA for response and recovery. So to a certain degree, most states, if not all the states, have a set program. When it comes to infrastructure systems, the response really starts local, and the utilities and mobility systems need to work with the local emergency managers and coordinate on when they need more resources. But it starts, if I understood the question correctly, the responsible party for making the repairs starts with the utility or the mobility agency. And if they're unable to fulfill those repairs or accomplish those repairs with the resources they have, they'll reach out to the emergency management agency, first the local. And if the local doesn't have it, then they reach to the next level, which might be a city, then a county, then a state, then the federal. And so at each level, if they don't have enough resources to provide to that utility or mobility system, which makes the lifeline, then they go higher until they get all of the resources they need. But response is local, and rarely would the federal agency completely take over the local agency, although when it has been completely incapable, that has happened occasionally. The state or the federal agency might need to step in. But what I want to point out, in addition to that type of a question, in addition, there are interstate, intercounty, and national level responses where electric power agencies from California might go to Florida for a hurricane, right? Because locally, the event might be so large that it overwhelms all the local stuff, and vice versa. So in an earthquake, you might see people, electric power agencies come from the Midwest or the East, all the way out to California, Oregon, or Washington, Utah, or something like that to help make repairs. So these organizations pre-exist so that it's easy to make a call. You don't, it's just a matter of these people mobilizing because they're already ready to go. Whenever there's an event, they wonder, am I going to be called out or not? Now, let me link that to the concept of functional recovery that Congress had requested these agencies to think about. Functional recovery is the idea of designing for restoration. So right now, just watching Terza, I'd just like to follow up on her excellent presentation. She covered a lot of this already, very concisely and well spoken. But what she's talking about is, given what the infrastructure is today, which wasn't designed, it may or may not have been designed for a major event. It may or may not have been designed for an earthquake, for example. Even if it was, it's not designed for when the services should be recovered. It's designed to protect public health and safety for the most part, but not when do they get recovered. So they get recovered when they get recovered. It could be a day, or it could be 6 months. Imagine 6 months without power. You can imagine a day it does occur and we don't like it, but imagine 6 months of those days consecutively. That's not very good. And we don't know. There is no target. So the concept of functional recovery is, how long does Terza need to do her job after the event? And what is acceptable? Is it acceptable to have a hospital without power for 30 days, for 60 days, for 100 days, 6 months? Think of what happened in from some hurricanes and in Puerto Rico. I think they're still recovering from Hurricane Maria and rebuilding the electric power system. So, and that was several years ago. It's not gone well. So the idea is, what is acceptable and how do we design for this? And we don't know how to design for it, but all of this has to work together. So we should be designing. We know that even though we design, we can't keep these complicated systems from being damaged. There's just no way. They're too large and too complicated. You can't do everything. but you can do your best, and you can target with the known and even the known unknowns. That's a concept of resilience, being prepared for what we don't know, and have a target time frame for when we recover, which has to account for all of these other things that I answered in relation to the question. So just trying to frame that in the context of functional recovery. So I'll stop there. It's a great question. Thank you.
For your answer. Teresa, you look like you wanted to add something. Would you like to comment on the same one?
Actually, so Dr. Davis covered most of it. And like he said in the presentation, that is, so to answer his question, exactly that. Our activation will be for the duration of the restoration. So for example, we had a recent nor'easter, which had us activated for 4 days straight. And conveniently so, my lead, the director, our lead engineer, was actually doing this emergency function from his home with no power. So at the end of the day, it does lead to this restoration time. It also leads to a lot of the public, wanting, it's a public outcry where they are asking for, how come the utility companies are not restoring me right now? So it is very difficult to try to mitigate that, but the communication is so important. And exactly like you said, if we can't speak to how the utilities are actually building this infrastructure because we are regulatory oversight, but we can do our best to try to implement these guidelines when we're asking for emergency response. So some of these major weather events have actually led to us pushing the utilities to have more rigorous planning, including things like vegetation management, to be able to kind of mitigate some of the damages that we anticipate depending on weather events. But for the most part, yes, planning is so crucial, and it affects all the way from the top of the chain down to the bottom. So but that's all I had to add on that.
Hey, no, thank you both for your input. With that, Dr. Davis, back to you. The question from our online audience. They ask, quantification of resilience is an important subject, specifically when we are going to engage stakeholders to make investment in resilient infrastructure. I'm just wondering which of operability or functionality are proper for resilience quantification.
Both. You need to be, you can't actually quantify resilience to an infrastructure system, my opinion, this is what I'm trying to preach, without quantifying both. You need to be able to restore and quantify the restoration of the services, which is operability, at least the basic services. And you need to, which by the way, is only achieved at a certain level of functionality, right? So you have to quantify functionality even to get to operability, because you have to make so many repairs to get the basic intended functions back and running so that you can get those basic services back and running. But that's not sufficient. They're temporary. Teresa actually talked about that in one of her slides, where she kind of distinguished the service part and then the post, I forgot the terms that she used, but the post service work. So things are put together with Band-Aids. They're doing everything they can to get the services back to the customers, and so that the customers can begin to resume their activities in a normal manner, relatively normal manner. But that doesn't mean the system. Now the customer might see the system's working fine, but in reality, it might not be. Remember, I showed that after the Northridge earthquake, it took 9 years to get the system working the way it was in Los Angeles, because some of those repairs were very extensive and very massive. But that didn't keep the system from working. So to get the system to operate in the reliable manner like it was before, or even more reliable, now that you've learned some things by some vulnerabilities from a hazard attack, it takes longer. So that's why you'll follow one of those functionality curves that I showed in one of the diagrams. Either you don't get it to where it was, you get it to where it was, or you make it better than what it was. But you have to follow both. So operability in this context is the support of a system, the system support to community resilience, getting the services so that the community can resume their relatively normal activities, get the economy going, get their society going. And functionality restoring it to all of the repairs is actually a measure of the resilience of the system itself.
I have another question, but I think before we get into that, Dr. Potts, could you comment on the seismology of the area and what kind of seismic risk are we subjected to here in the New England region?
Well, sure. So when we conduct our risk assessments, we generally rely on USGS. They have an online unified hazard tool, a design guide that gives us the basic information we need for a risk assessment. In general, New England doesn't have very high seismic hazard, but it has some. And if you look at the seismic hazard maps, you can see areas such as central New Hampshire, which might have a slightly higher seismic hazard. When we use that USGS tool and do a deaggregation of seismic hazard, you can see it's distributed like a background distribution throughout the model. And that's something we commonly see in the central and eastern United States. Makes it more interesting here, I think, than in the western United States, but it also makes it more challenging when you don't have specific active or capable faults to attribute your seismic hazard.
So when considering lifelines with multiple sites or continuous lines, how should probabilistic methods be modified to account for the risk of a specific ground motion occurring in one of multiple locations or along one of the locations for a continuous line? Most PSHA account only for the probability at a single site.
Well, that's for two of us, but I will, let me take the first shot, Dr. Potts, and then you can add. Something that I've been thinking about for a very long time, and a few others have as well. It's a very insightful question. So if you're using the USGS or ASCE 7 maps prepared by USGS, you're only getting data or information at a single location. That's what this question is referring to. But understand an infrastructure system is widely distributed over large areas, sometimes multiple states. And but these maps that are used in seismic design are really intended for a single site. It's thinking about a building. It's just a building. And think of a building as a single component. Lifeline systems have buildings. And even though the building is a system, think of a lifeline system of systems of systems of systems of systems, right? Just they're layered. And so that building, which is a system, is just a component in the context of the larger system. You think of it that way. And so, yeah, you can design that component, but is it designed consistent with the rest of the system? And so what needs to happen to get to the core of the question and give an answer to it is, we need to be, how does that have to change? We need to change by thinking of probabilistic scenarios. So what is a scenario that will affect the entire system so that we know how the system will actually function and be able to provide its services? So it's a little bit more difficult because there's an infinite number of scenarios. And so how do we select those? I don't know. That is a problem that has not been solved. There are some very intelligent minds working on it. And right now, when you're trying to apply it, it's very complicated. So complicated that mostly no systems can actually implement it in a normal manner like you would for a building. You can go to the USGS maps. You can pull down your hazard parameters, design for those, and move on. But now you got to analyze the whole system based on a scenario. And then how do you do it for all the probabilistic scenarios and the probabilistic fragilities for an entire system to understand where it would be damaged, what isn't working, if what's based on what's not working, what services can be provided, how long can you restore those services? All of these things really need to be thought about to bring it into this concept of operability and functional recovery, and then full restoration of function. So I'll leave it at that. And if Dr. Potts wants to add anything to that.
Oh, thank you. Yeah, that's an interesting question. So here in New England, most of our flood risk management projects are dams, embankment dams. So we don't have that linear aspect, but our sister districts and divisions with miles and miles of levees along the Mississippi River system or Missouri River system, perhaps they have less seismic hazard unless they're within that New Madrid zone. And the structures associated with those levee systems, that is an interesting, difficult question.
So I have another question, and this is for you again, Dr. Potts. It is, when assessing risk to your dam/levee portfolio, what are you looking for? What visible signs or what, I guess?
Well, during our risk assessments, we prioritize life safety risk above the economic risk. So paramount is always life safety risk. So we're always looking at life safety consequences prior to economic consequences. And we conduct potential failure mode analyses and then a semi-quantitative risk assessment on that. So we look node by node at a potential failure mode analysis. And that's our general approach to risk assessment.
I have another question. I guess this is Tirza. Do any action lists or framework exist for post-disaster recovery or operability and functionality of Lifeline systems? Is this approach similar in each state?
So I can't speak to any other state. I can only speak to the state of Massachusetts, but primarily as we are, again, regulatory oversight, we can provide guidelines within that emergency response plan that would address things in the event of a catastrophe, but in terms of the actual infrastructure and the implementations made to safeguard against these events, that would lie in the hands of the utility themselves, whether they are just the distribution companies or whether they actually own infrastructure, including like transmission as well. I'm sure that federal regulatory agencies, as well as the Independent System Operator for New England, ISO, would have regulatory guidelines that speak to the actual buildings, the built infrastructure. But as the DPU, we can primarily focus on the safety, the operability and functionality, more so as it pertains to the customer and the restoration of those critical lifeline systems.
Another follow-up question. I believe this is, 1 second. Okay. Are there any functional recovery considerations for designers to be aware of in the context of non-critical buildings and infrastructure? And for the audience, if you could just direct the question to a panel member or leave it as for everyone, that would be nice. Thank you.
I'll take a shot at that one. So I could see this question coming from multiple perspectives, and I'm not exactly sure which one the requester was coming from. So I'll give a few perspectives. So one, functional recovery or designing for recovery objectives, which is really what it's all about, is a new concept. So codes or standards for the most part, there might be a few things, but they would be relatively few, very few, that actually address designing for recovery in buildings especially, but also in infrastructure. So there's not a lot out there, but based on the request of Congress to look at this, there are projects underway that are working on that. And those projects address critical and non-critical buildings. So there's stuff coming. And it's going to take a while to get it oriented and situated into how this fits into building codes and standards and so on. So that is just initially being addressed. But there are You ask about considerations. Yeah, there's a lot of considerations that can be done. The code is the minimum. So you can think about what does it take and what should be prepared. You could do your pre-planning. You can have a lot of planning objectives in advance, being able to, the word, the phrase is not coming to me. Maybe Terza could help me, but there's there's a lot of planning for keeping your business open after the fact. Right. So how do you manage what are your priorities for recovering as a business? For the infrastructure itself, you could plan and help work with, how do I keep at least an elevator in a high rise working? So that would be part of a concept of functional recovery. So you can design beyond code with the idea that things will work afterwards. So if you wanted a non-critical building, like a non-hospital or non-emergency operations center, just a regular office building, but it's an office building that's really critical for your function of your company, you could design it to risk category 4, and that probably might meet functional recovery objectives. It might cost you a little bit more, not necessarily a lot more, but it probably would cost you something more. But that's the way that you could address non-critical things. You could actually think about it as being more critical for the purposes. It might not be critical for all of society, which is what risk category 4 is generally used for. But an owner has the opportunity to decide that it's that critical to me or to my company, and design at a higher level. And some of those concepts are being addressed as part of this research I referred to at the beginning of the answer.
Are lower seismic regions more susceptible to damage and higher recovery times to earthquakes due to infrastructure not being designed for extreme events?
Since there's no volunteers, that's a loaded question, but I'll take a shot at it. One, I would say if you use the term earthquake, and if it's of importance, it is an extreme event. So understand that in context. And so that's the way I will begin to address it. I think you have to think about this in terms of all things being equal. So you have, just think of an infrastructure system. I'm a water system guy, so I'll think about it in terms of a water system. So think of a water system that's built, and that same water system could either exist in a low seismic area or a high seismic area. So maybe you think of Colorado or Maine, the lower seismic area, and Los Angeles is a high seismic area. Same water system. But now as you're designing that water system that has the same layout, you would have different design criteria in Los Angeles than you would in Maine, right, or New Hampshire. That's the way I think we would need to think about it. So your system, your connections might be lower or weaker, and your buildings might be designed to a lower criteria based on probability. So now if you have, you can have a magnitude 6.5 earthquake in either location. In New Hampshire or Maine or someplace in the Northeast, you would have, in the New England states, you would have a lower probability of that magnitude 6.5 earthquake occurring. So your design loads per the code would be lower, or per standards, than in the New England states than it would be in California. Now, if that magnitude 6.5 earthquake occurred on both of these systems, the result you would expect that the New England design would be more fragile to the same ground motions, then it would have more damage. However, if you actually understand the seismicity, maybe Dr. Potts would like to fill in something here, but if you understand the seismicity, the shaking in New England for the same size earthquake might actually be lower. Right, so it's a nonlinear problem in trying to answer this. So that's why I said it's a little bit loaded. So you might think that that's the case, but that's not necessarily always the case. there's a tremendous number of factors relative to that. Do you have liquefaction? Do you have landsliding? I mean, all these things come into play. So it's difficult to just say yes or no. But the bottom line is that we should do the best we can, and always try to design with what you can afford to design to withstand these earthquakes, no matter where you're at. Earthquakes can occur anywhere, as we have found. And if you're providing services to critical customers, you should design to a higher level, because the consequence when that event does occur may be unacceptable if you're not designing to a higher level for the critical facilities.
I believe we have one final question, and this one goes to Tirza. It says, what were some previous crises that caused major disruptions to critical lifeline infrastructure systems in Massachusetts? And what were the lessons learned?
Okay, so just in my experience, because I haven't been with the department too long. So just an example, and I said I draw from recent events with our recent nor'easter. It was the first time that I personally with the department experienced a situation where we had almost 500,000 customers without power in the state of Massachusetts. So that was, even though it was only listed as an ERP3, it was pretty sizable. There were not, like, this was a situation where, you know, with the weather forecasting, you can only prepare so much. So you can declare what you anticipate is going to be the level of damage, but essentially, once the weather event actually happens, the duration of that weather event may change. And then also it goes into the duration of how soon can we get buckets in the air to actually restore? How soon can we get somebody? A lot of times, you know, in a seismic situation, obviously underground infrastructure would be affected. So, you know, how you have lines next to gas pipelines as well. But in a normal operation for the vast majority of the distribution system in Massachusetts, it is overhead lines. So, you know, understanding that these weather events, even though it might be categorized as just, you know, a one-day event, it could easily spill over into 2 or 3 days just because the weather system has not exited. So in a situation, again, like with an earthquake, obviously that is going to be catastrophic damage that is going to require multi-day restorations. But at the end of the day, the lessons learned will always be if there is some sort of disruption. So for example, we did have a hospital that was out. It was on temporary generator. We had to then, you know, put that as a priority list. That is a critical facility. It gets restored. The communication of that restoration has to come from those who actually restored the power, and then bring it all the way back to state level where we can report that to MEMA and say, hey, this hospital has been taken care of. So a lot of the lessons learned really do surround communication, because we are not the boots on the ground. So we are not the ones literally in the bucket making that restoration. So having that visibility around there and having that communication is vital. So lessons learned will definitely come. As I mentioned in my presentation, I stated some of those catalyst events, weather events that created guidelines and regulations that we then implemented in the requirements for filing the ERPs, which is the emergency response plans by the power companies. But so yes, lesson learned always have to do with, like, you know, what are the variabilities? What are the potentials for weather events to turn into actual incidents? What are the likelihood of impacts to the system based off of each type of either weather event or emergency event in general? So yes, lessons learned will always be, for the department, they will be basically communicated through the guidelines and regulations that we then implement or require the utilities to provide to us annually.
And with that, I would like to conclude our panel discussion. Elizabeth, if you'd like to take over.
Great. Thank you again to all our speakers and to everyone who joined us today, and especially to the New England chapter and the student chapter at University of Massachusetts Amherst for organizing this event. A recording of this webinar will be available to view on the Matchbox platform for several weeks, and then thereafter on EERI's YouTube channel. You'll get a follow-up email, which will include a link to a post-webinar survey, and we'd really appreciate if you could take a few minutes to share your feedback with us. Finally, we'd like to thank FEMA for supporting this webinar and also EERI's members for helping make events like this possible. If you'd like to learn more about EERI, there's our website on the screen and information on how to join. Thank you.